Today we'll be talking about LangChain. Now what is LangChain? LangChain is a framework for developing applications powered by large language models. Now let's understand by taking an example. Let's say you have a PDF which contains 600 pages. Each page you can see you have information related to dogs. So this is one breed, this is another breed, and this is the third breed. So similarly, you have information related to different kind of dogs in this PDF. Now if I say find the information of an American bulldog, so what you'll do, you'll go through this PDF, you'll find the chapter, then you'll find the information related to American dogs. So instead of doing that, if I say let's build a system where we'll give the PDF as input and we can chat with the system, we can ask question to that system and it will do the work automatically. It will find the information from this PDF and it will give the accurate answer that we need. So the general pipeline for building this system will be like this. We have our PDF, we'll load the PDF here, then we'll split the PDF into smaller chunks, then we'll create embeddings and we'll store those embeddings in a vector database. After that we have our query, we'll convert this query into embeddings and then we'll retrieve the relevant information from this vector database. After that we'll combine the result and our query, we'll create the prompt for our model, for our LLM, and then we'll get the output from our model. Now here you can see we have a lot of components. Here we need to figure out how to load the PDF, then we need to figure out how to create text chunks, how to create embeddings, how to interact with vector database, then how to do this retrieval operation, then how to create a proper prompt for our model, and then how to parse the model output. So how to understand the model output. You can see there are a lot of moving components here. So in one way you can design all these components by yourself, but here you can see to deal with each component has an input, has an output. So if you want to write function for each component, you need to take care of those inputs and output formats. Let's say you have one best embedding model right now. Let's say after 1 year or after 2 months you find a better embedding model. Now to switch that model, you need to take care of the functions which are working with inputs and outputs to integrate this model. Same thing if you want to switch the vector database, if you want to switch the retriever or the model which is creating the prompt or the model which is passing the output. Even if you want to switch the LLM, let's say you are using ChatGPT now but you want to use Claude. So in this case the input and output or the interaction, the way we interact with this kind of components, they will change. So LangChain takes care of all these components. It has something called document loader to load the PDF. It has something called text splitter to split the PDF into chunks. It has something called embedding model to create the embeddings. It has a way to deal with this vector database. It has a way to deal with this retriever, to create prompts, to deal with different kind of LLMs, and to deal with the output. LangChain is saying you focus on your work, you focus on your pipeline. We have all the components to build your pipeline. So I hope you understood the role of LangChain in this context. Now what can you do with LangChain? In LangChain we can build chat with PDFs, we can build customer support bot, AI coding assistant, legal document analyzer, voice assistant, financial report analyst, meeting summary generated, and so on. So these are some examples that we can build using LangChain. So in this series we learn each component one by one. Now let's set up LangChain in our environment. So first create a new environment. we are creating the new environment as LLM, and we are using Python 3.10. After creating the environment, we are installing all required libraries. After installing all the requirements, here we are creating API keys for OpenAI. If you don't have any account, create an account, and then you can create your own API key. Now you can copy the API key which you will be using in your project. Today we'll be talking about document loader. Now in our pipeline we have document loader here. A document loader is the component that helps you load raw data either from text files or PDF files or websites or different sources into LangChain as documents, and each document object has page content and metadata. Page content has the actual text and metadata has the metadata related to the text. Now if you go to this link, you can see a lot of different document loaders. So here these are for web pages, these are for PDF files, these are for cloud providers, and so on. But here we'll be talking about text loader, PDF loader, directory loader, CSV loader, and web-based loader. So what is a text loader? Text loader is a document loader that is used to load plain text file or .txt files into document objects. So here we have the docs.txt file, you can see. Now we are using that file to load here. Now here we are using text loader to load the docs.txt. Now let's run it without any chat operation. So if we run this Python 1, you can see we have successfully loaded the content of docs.txt into LangChain, and you can see we have metadata and then we have page content. If you check the type of these documents, you can see this is a list. So this is a list of documents. Now if you put 0 as an index, we'll get this information, page content and metadata. If you do .page content, we have only page content, and then if you do .metadata, we have only metadata. Now remember in the previous video we have created an OpenAI key. Now put the OpenAI key into a .env file like this, and here when we are doing load_.env, it is loading that key into the environment, and then we can use that key to chat with the OpenAI. So here here we are trying to chat with this doc.txt file. So we are loading the OpenAI, you can see, and we are asking find the height of each doc from the dog essay, and for dog essay we are giving the page content of docs 0, you can see here. So if we run this cls python, if we run this, you can see we have answers from our LLM. So in this way we are loading the txt file into LangChain and we are using the chat OpenAI. The next document loader is the PDF loader, and we use this loader to load PDF files. So here we have a PDF file, beagle.pdf, and this file has contents like this, you can see. So here we are using PyPDF loader to load the PDF, and if we run this, Python 2. You can see we have successfully loaded the PDF here. Now if you see here, we have length that is 30. This is because this PDF file has 30 number of pages. So when we use PyPDF loader, it loads each page as a separate document. That's why we have 30 number of documents here. Now the next document loader is directory loader. So directory loader is a utility that loads multiple files from a folder. So here we have this folder which contains 3 PDF files. Now here we want to load all these PDF files. So here we have directory loader. You can see we are giving the folder name, so part to this folder, and then we are giving this extension .pdf. So when we run this, you can see 1, 2, 3. So it has loaded all the PDF. And if you see here, we have 90 number of documents. This is because each PDF has 30 number of pages. Hence 3 PDF, 30 into 3, 90. So we have 90 number of documents here. Now let's say you have a CSV file. So we have a CSV file here. Now if you want to load this thing as a document, for that we have CSV loader, and here we are loading the CSV file. If we run this cls python 3.4, you can see we have successfully loaded the CSV file, and you can see we have 359 number of documents. This is because CSV loader considers each row of the CSV file as a separate document, and this CSV file has 359 number of rows. Now after that we have web-based loader. So web-based loader is a document loader that fetches and loads content directly from web page. So here we have this web page and we want to load content from this web page. So here we have web-based loader. We are giving the URL to that web page, and when we run this cls web, you can see it has successfully loaded the content of this web page. So we have seen text loader, we have seen PDF loader, we have seen directory loader, CSV loader, and web-based loader. Let's say you want to design your own custom document loader. For that you can use the base loader class, and then you can design your own custom document loader. If you want to know more about this custom document loader, you can go to this page. So here you will get all the information to build your own document loader. Today we'll be talking about text splitter. So text splitter we have here in our pipeline, you can see. So what is a text splitter? A text splitter is used to break long documents into smaller manageable chunks. So why do we need text splitter here? Why do we need to split larger document into smaller chunks? If you look at here, you can see we have a max token limit for all of these models. That means input to these models will be lesser than this max token limits. This is one reason why we need to we need to split our documents into smaller chunks, so that our input would be lesser than this max token limit. Second reason is, it has been observed that if we create embeddings with larger document, the quality of embeddings will be poorer. It will be very poor as compared to the embeddings with smaller documents. This is the second reason. The third one is, let's say I will give you a book and I will ask a question. So let's say this book has like 600 or 1000 pages. So if I give you a book and ask the question directly, what you will do, you will go through the book, entire book, and you will try to find the answer for that question. And this will take too much time because you need to go to the book to find the location of that particular topic and then find the answer. But if I give you 2 pages and I'll ask you the same question, you'll be able to find the answer faster. So if you compare this with text splitting, you can see this is the whole entire text, and here this is the splitted chunk. When we deal with smaller chunks, the performance of our model will be faster because smaller data, and the resources that are required for this operation will be less. Hence, we are saving cost also. And in LangChain, we have length-based splitter, we have text structure-based splitter, document structure-based splitter, semantic meaning-based splitter. Now, what is a length-based splitter? Length-based splitter in LangChain that splits large documents into smaller chunks based on a fixed length. This fixed length can be of character count or token count. So basically, if we have this text, you can see we have 3 paragraphs, and we'll give chunk size that is 25. It will split the text by counting 25 number of characters. Each chunk has 25 number of characters. Now here you can see loyal, so L is in one chunk and OYAL in another chunk. In this way, this doesn't make any sense. We are losing the information, right? Because this is not a good quality chunk. So to deal with this kind of issue, we have something called chunk overlap. And if you do that, we are taking a 5 number of characters as chunk overlap. You can see chunks are overlapped here. So most L is in one chunk. Similarly, this loyal, the second chunk starts from here. So in this way, we are capturing good quality information. We are capturing more information as compared to the operation we are doing in this case. This is how we'll be using character text splitter. So here we are loading the data, then we are setting up character text splitter here. We have chunk size 0 and we have chunk overlap that is, we have chunk size 100 and we have chunk overlap that is 0, and here we are taking 10 as chunk overlap. So if we run this Python, you can see, so this is with 0 overlap and this is with 10 overlap. You can see here. So here we are not trying to find out the structure of this paragraph or this text. We are not trying to find out the meaning of the text. We are just counting the number of characters and then we are splitting. In the next text structure based splitter, here it follows a hierarchy. It follows the natural language structure. You can see if we do use this thing, it will split the text based on paragraph first, then sentences, then words, then characters. So here we have this example. Now first, when we give this example to text to the splitter, it will split the text based on paragraph. You can see, so 3 paragraph, we have 3 blocks here, and here we are taking chunk size as 10. So here after that, after splitting with respect to paragraph, it checks the length, it is clearly greater than 10, then split the paragraph, each paragraph with respect to sentences. You can see, so from here we have 2 sentences. Here also the length is greater than 10, so it splits the sentence with respect to words. You can see here all of these are like less than 10 except independent word. So it split the independent into 2 chunks, and then it tries to combine these words. So you can see after performing this splitting with respect to character, it combines 2 words and it checks the length, whether the length is satisfied or not. So here cats and R are combined. You can see then independent is split into two chunks. You can see independent 1 and T is in the next chunk, and then T and animals are combined here. Similarly, this is for block 1 process. For block 2 we have this, and for block 3 we have this. So finally we have these chunks out of this text. Now let's see in code. So in text structure based, we have recursive character text splitter. It will perform the same task, and when we run this, You can see we are getting the same chunks here. Now this is our third text plate splitter. So here this document structure based text splitter, it will split the document with respect to their type. That means here the input text is a string, and here you can see we are loading the text from a docs.txt file. So text can be of any type. It can be in a JSON file, it can be in a markdown file, it can be a Python code file. So for different kind of text structure, we have different kind of splitter. So it is the same recursive character text splitter, but with markdown version. So here this is our markdown text, and when you use this thing, we will have chunks like this. Similarly, when we have Python file, you can say this is a Python code, and we are using recursive character text splitter Python version, and then we are getting the chunks like this. Let's see in the code. So here we have text structure based done document with respect to markdown. So this is a markdown format, markdown text, and when we run this 3 Python 3, you can see from the markdown text we have this chunks. Now let's run the next document based on Python file. So Python 4, and you can see we have this split. We have splitted the Python file like this. So this is the code. Same thing, we are using recursive character text splitter from language, and here we are giving Python as the language. Up to this point, we are trying to do the splitting based on either character count or based on the natural language structure, but we are not able to capture the semantic meaning of any text. So semantic meaning based text splitter, it split or it creates tokens based on the meaning. Now let's understand why it is different from the other. So let's say we have this text: dogs are loyal and friendly animals. They love to play and interact with humans. Cats, on the other hand, are more independent and curious. So in this paragraph, we have 1, 2, 3 sentences. First 2 sentences we are talking about dogs, and the last sentence we are talking about cats. When we use recursive character text splitter, you can see it will give results like this. So here if you will see, this chunk has information related to both cats and dogs, and here also same thing. So if we use semantic meaning, it will create the chunk up to this point rather than taking the whole paragraph. You can see this is not a good quality chunk, or we are not retaining good quality information. We have a mixed information here. So to deal with this kind of issue, we have semantic based text splitter. So how does it work? In semantic based text splitter, it calculates cosine similarity between 2 sentences. You can see cosine similarity between S1, S2, S2, S3, S3, S4, S4, S5. Then it calculates the standard deviation of this cosine similarity, and if any cosine similarity that is more than n standard deviation, n can be 1 or 2 or 3. So if we take n equal to 1 and a cosine similarity is greater than 1 standard deviation, we'll create that point as the split point. That means we'll be splitting the document at that point, just like this you can see. So this example of ours will have chunks like this. Now let's see the code. So here semantic meaning, we have this semantic chunker, and here we are like giving the embedding model of OpenAI. We are saying that breakpoints should be based on standard deviation, and here we are taking 1 standard deviation. So now when we run this, so we have chunks like this here. So guys, I hope you understood what is a text splitter. Today we'll be talking about embeddings. In our pipeline we have embeddings here and here. So what are these embeddings? Embeddings are numerical vector representation of text that captures the semantic meaning of words, sentences and documents. Now let's understand by taking an example. You have this document stored in our database and you have this user query. So in SQL kind of database, when you get the user query, you try to search relevant information by doing keyword matching. And you can see clearly if you do keyword matching here, the result will be none because the keywords are different. So what is the solution? If we can capture the meaning of these two sentences, you can see they have similar meaning. Then if we search based on the meaning, it will be easier to find this document. Is that we'll convert these two sentences into vectors and then we'll find the similarity, cosine similarity between these two vectors. So you can see this is our document and this is our query. You can see we have a good cosine similarity score. So embeddings enable us to do this similarity search. Now another requirement is that we need to convert text into numbers because our computer, it doesn't understand text directly, it understands number. That's why this embedding solves two issues. One, we need to convert the text into numeric numbers, and two, we need to present in such a way that it should capture the meaning of the text, and this vector representation is called embedding. So here we have these documents and we have this query, you can see. So we are using this model to create embeddings and we are creating embeddings here. After that we are doing a PCA to reduce the dimension to 3 and then we are plotting here. So if I run this Python, so here we have our documents in a 3D space and you can see we have a cosine similarity of 0.61 between our user query and this vector. So this is, you can say this is dogs are loyal. So dogs are loyal, this is the fifth number of vector, and if we check the fifth number of document, you can see 1 2 3 4 5 dogs are loyal animals that help humans emotionally and reduce stress. So out of all these documents, we can see this sentence or this document has the similar meaning. Today we'll be talking about vector stores or vector database. So we have vector stores here, you can see in our pipeline. So what is a vector database or vector store? Vector store is a specialized database designed to efficiently store, manage and query vector embeddings. In the previous video, we learned the concept of embeddings. So basically, embeddings are high-dimensional numerical representation of either text, images, audio or any other data type. By using these embeddings, we can do similarity search, which will be very helpful in our case. We need something to store those embeddings and to do this search operation, and vector database helps in this area. So vector database, it helps in similarity searches. It also, we can store metadata with respect to each vector, and it is designed to handle billions of vector and perform searches with very low latency. Let's take an example. Let's say we have 100 Docker articles and we store that this information in a SQL database. So we'll be storing we'll be creating columns like title, author, content, data. If we have this question, find all articles by John about training dogs. So hence we are storing the information about each author. We'll be doing this filtering and we'll be able to find the relevant information from SQL database. But if I ask you this question, what should I feed my puppy? So this is, this won't fall in this kind of column. To sort this question, we need to first understand the data, the meaning of data that we have in our SQL, and we need to understand this, understand the meaning of this question, and then we'll find the data which will be in the similar, which will be semantically similar. So we cannot perform this semantic search in our SQL database, but in case of our vector database, we have the vector embeddings which represents the data in a numerical format, which captures the semantic meaning. So by using vector database, we'll be able to find answers like this: puppies need high protein diets with essential nutrients. So this is the difference between SQL database and vector store. Also, we can use any of these indexing strategies to do good quality search in less time. Now in LangChain we have this local or in-memory vector stores, that means offline vector stores. So we have Face, we have ChromaDB, we have Deep Lake. We also have cloud-based vector stores. We have Pinecone, VV8, Quadrant, Milvus. So you can use any of this vector store. So these won't be chargeable, but I think they will charge some amount of fee if you want to use their services. We have your Face vector store. You can see while loading the PDF here, then we are using recursive character text splitter to create chunks. We are using OpenAI embeddings. Then we are storing all this information in a Face vector store, and then we are doing a similarity search here. So if we run this Python, you can see it is doing all of this thing, and you can see after doing a similarity search, we have these documents. Similarly, here we have ChromaDB. You can see same thing. We are loading the PDF. We are splitting into different chunks. We are using the OpenAI embedding here. We are creating the vector store here. We are using the ChromaDB here. Then here we are doing the similarity search. So it has loaded, and you can see it has created this vector store. Query and retrieve documents, top 3 relevant documents. So here we have retrieved relevant document to our query, and then after that here we are extracting documents, embeddings and metadata. So this is the print statement for that. Document 3 and metadata, and then here we are these are for before update. So before update, you can see we have this value, and then after update we have this value. So after that, here we are adding the new document added. Today we'll be talking about retriever in LangChain. So in our pipeline we have retriever here. You can see now the retriever is a component that fetches relevant document from a knowledge source. This knowledge source can be a Wikipedia, can be a vector store, can be a dataset, database, can be anything. And here we'll be talking about Wikipedia retriever, vector store, MMR, contextual comparison retriever, multi-query retriever. Now what is a Wikipedia retriever? Wikipedia retriever is a retriever class in LangChain that fetches relevant content from Wikipedia. So these are some options that are available in this Wikipedia retriever. So here we have Wikipedia retriever, and if we run this, you can see it is searching the Wikipedia, and it has returned 2 documents because we have written top k results equal to 2. Hence, it has written two relevant documents for this question, that is what is a beagle. You can see here. Now, the next type of retriever is vector store retriever. Now, this retriever is a wrapper around a vector database and it retrieves document from a vector database. So you must be thinking, why do we need this retriever when we have similarity search? Here in the previous video we have seen this code, this ChromaDB code. So here you can see we are doing a similarity search and we are getting the relevant documents. So if we have this similarity search, why do we need a vector store retriever? With vector store retriever, we can do a lot more than just similarity search. We can do metadata filtering, we can do custom scoring, we can easily plug it into into LangChain pipeline. We can create multiple, we can compose multiple retrievers. We can write custom retrieval logic. Hence, this is a better option than just similarity search that we have in case of vector database. Now, let's see how it works. Here we have vector store. So first we are reading the PDF here, then we are splitting that into multiple chunks, then we are creating the vector database. You can see we are creating the vector store. Now after creating the vector store, we are using this. We are using the vector store as retriever like this, and here we are saying we need top 3 results or top 3 documents. And when we run this, you can see created vector store. Now you can see we have top 3 relevant documents. So this is how vector store retriever works. Now next we have MMR. MMR stands for maximum marginal relevance retriever. When you use this technique to retrieve documents, the documents will be relevant and diverse. Let's understand by taking an example. Let's say we have these documents in a vector store. Now we have this query, how do dogs help with anxiety? So if we use this without MMR, we might get something like this. So dogs help reduce anxiety by offering companionship. Dog help reduce anxiety by offering companionship and being by your side during tough times. So you can see these two are same. You can see word by word these two are same. So we are getting relevant document, but these are not unique. So to get relevant and unique document, we use MMR technique. So when we use MMR, we'll get separate document. You can see all these documents are relevant and all these documents are unique, and it scores using this formula. You can see here higher lambda value will give more relevant document, lower lambda value will give more diverse document. Now here we have code for MMR. So similarly we are creating the vector store here. Then while retrieving, we are using search type equal to MMR. So this is the difference between MMR and without MMR. You can see. So when we run this, loading PDF, creating vector store, and then we are getting unique documents. You can see here. Now the next type of retriever is contextual compression retriever. So contextual compression retriever is a special kind of retriever that compresses or filters the received document based on a user query to return only the most relevant part of each document. Let's understand by taking an example. So we have these documents in our dataset or in our database. Now this is our user query. What does a beagle look like? It might return something like this. Beagles are small hounds with tricolor coats. They were bred in England for rabbit hunting. You can see this is the appearance info and this is extra info we have. but we need only appearance info, right? This is just a noise. Similarly, we have here, this is appearance info and this is extra info. So when we use contextual compression retriever, it compresses or filters out this extra info. So from here, from these kind of results, we'll be having this. So beagles are small hounds with tricolor coats. So we are keeping only the information that are relevant to appearance. So the pipeline for this contextual compression retriever will be something like this. We receive the user query, we create the base retriever, then after that we retrieve the relevant documents, then we'll pass that to a compressor and it will remove unnecessary information and it will keep only relevant information with respect to our user query. And the compression happens by using an LLM. Same thing, we have documents, then we are creating a face vector store. Then here, this is the vector store with similarity search, and now here we are creating the compression. We are creating the contextual compression retriever. You can see it is using a LLM as a compressor. You can see here. Now when we run this Python 4, so this is like without compression. You can see we have extra info. After compression we have only relevant info. So this is how this contextual compression retriever works. Now the next type of retriever is multi-query retriever. Multi-query retriever is a clever and powerful tool in LangChain designed to improve the recall of your retrieval system by leveraging LLMs to generate multiple diverse and semantically similar queries from a single user query. It then performs retrieval for each of those queries, merges and deduplicates the results to provide a richer and more complete answer set. Let's take an example to understand this. So if we have this question, what does a beagle look like, and this one, describe the physical appearance of a beagle. So they both talk about the same thing, that is the appearance of a beagle. So user can ask either this question or this question. And the second thing is, this question has multiple interpretations. So this can be describe the physical appearance of a beagle, this can be what are the visual characteristics of a beagle, this can be also how can you identify beagle dog by its looks. So same question has multiple interpretations. To deal with this kind of situation, we have multi-query retriever. So here this receives the user query, this generates multiple queries out of this user query which will be having the similar meaning, and then after that it does the retrieval, and after retrieving document for each query, it merges everything together, it removes duplicate documents, and then finally give the result. So this is the workflow of this multi-query retriever. Now here you can see these are the documents. We are creating face database again. Now here we are using LLM to create multiple queries, and then all the processes that merging and deduplicates happens here. So if we run this, you can see this is without the multi-query retriever, and after using that we have these results. That's it guys. I think you got a better understanding of retrievers in LangChain. Today we'll be talking about prompt in LangChain. So we have prompt here in our pipeline. Now prompt is the input to our LLM. It's how we are communicating with our LLM. It can be a simple question, it can be an instruction, it can be a request. Now prompt template is a reusable structured way to construct prompt. So basically here we have this prompt or LLM. You can see this is a string. Now let's say you want to switch the instruction. You can see from please summarize the following text to write an essay on the following text in 50 words or 100 words. So to do that, you need to write the prompt again entirely with the new instruction. Let's say you want to change the text here. To do that, you need to write the entire prompt again. In case of prompt template, we just have to create the template just like this. You can see we can switch the instruction with this placeholder. We can switch the text with this placeholder, and same thing we can do for output format. So we'll be using the same template. We can switch any value with respect to our requirement. So this is the basic difference between prompt and prompt template. Now in LangChain, we'll be discussing prompt template and chart template. So prompt template is designed for models that expect a single and continuous string as input and produce a single and continuous string as output. These models are often referred to as completion models or text DaVinci 003 style models. So basically we are giving a string as input and will be receiving a string as output. So here you can see this is the code. So create a 20-word summary on dog using dog essay. So these are placeholders and we can pass any value to those placeholder. Now let's see prompt template in action. This is the main article, and here please provide a concise 50-word summary of the following news article, and here we have article text as placeholder. So while using this, we are passing the news article through this article text, and if we run this, our final prompt looks like this. So it will be please provide a concise 50-word summary of the following news article, and here we have the entire article. And if we check the class, this is the string. So this is a single string input, and when we pass this to an LLM, it will produce a single string output. Next we have chart prompt template. Now chart prompt template is specifically designed for chart models like OpenAI's GPT 3.5, GPT-4 and other models fine-tuned for conversational interface. These models are optimized to understand and generate responses based on a sequence of messages, each attribute to a specific role. So the role can be system, human and AI. So a system message means it is used to set the overall behavior and instruction for AI. Human message, this is the input from user. AI message, this is the response we get from our AI. And placeholder message, so here using this placeholder message we can insert dynamically a list of messages. This means we'll be able to insert history, the chart history into our prompt. Now you can see here this is an example. So here this is the system message. You are an expert news summarizer. Your task is to provide a concise summary strictly limited to 50 words, ensuring accuracy and neutrality. And human, where is the news here is the news article to summarize. So basically here we are setting up the role, we are inserting the model that how it should behave, and here we are giving the user query. Now let's see this in action. So here we have chart prompt. You can see this is the article, and here we are setting the instruction for the behavior of our model, and then here we are passing the user query. Now when we run this, you can see this is the complete prompt. So here we have a system message, we have a human message, we have other metadata here. Now here when we loop through this, we'll be having this human role is equal to system. Here this is the behavior that we have provided, and then human role is human. Then here here is the content for this role. Now this is how chart prompt template works. So the basic difference between this and the prompt template is that here we can assign role based, we can introduce history in our prompt. In prompt template we don't have any role based instruction, we just have the entire query with placeholder. So benefits of chart prompt template over prompt templates are chart prompt template has native support for chart models. Nowadays everybody is creating chart models instead of completion models. Now it has explicit role based context, it has like explicit role based instruction, so that helps a lot in case of to control the AI behavior, to control the output. Now here we will be able to use this message placeholder to introduce history in our prompt. So this is beneficial because in this way the model will able to have the entire context of the conversation, so that it will be able to easily answer the required questions. Now these are the same thing here. The prompt template we have like string with placeholder. In chart template we have like role based messages. Here this casts to a string and this casts to a base message objects, and here this is suitable for completion models and this is suitable for chart models, and it has role awareness, and here we have to enter the history manually in this prompt template. But in case of chart prompt template we have something called message placeholder, where it is very easy to integrate history in the prompt. So here we will be able to control the AI behavior in a limited way, but here we have a higher degree of control over the behavior. Now this is an example of message placeholder. So this is a special component used inside chart prompt template that allows you to dynamically inject a list of chart messages. So let's see this in action. So here we have this chart prompt template, you can see, and we have message placeholder. You can see this message, this system message is here, and then here this is the chart history, and then if we write again, tell me about Beagle. So this is the prompt now, you can see. So here we have AI messages and then we have human message. So this is the current message and we have our history here. So this is the human message, hi, then we have our response, that is hello, how can I assist you today, and then we have this current query, that is tell me about Beagle, and then after that it gives the answer, and then it will be appended in the chart history and it will be provided in the next prompt when we use. So here let's say beautiful, you can see. So this is getting appended again, tell me about Beagle, we have this AI response, then here human message, we have beautiful. So you can see it's very easy to integrate history in this conversation using placeholder, this message placeholder. Today we'll be talking about models in LangChain. So models, we have embedding model here and here, then we have our main model LLM here. So basically the model component in LangChain is a core part of the framework designed to facilitate interaction with various language models and embedding models. So in model component we have language models and embedding models, and language model is further divided into LLMs and chart models. So these LLMs we can call them also text completion model. So here we'll be giving string as input and we'll be getting string as output. In case of chart model, we'll be giving a list of role based messages and we'll be getting message based response. And in embedding model, we'll give string as input and we'll get numerical vector as output. Some examples for this LLM or text completion model are Text DaVinci 003, Command X Large, Claude version 1, GPT-J, Falcon 7B, Llama 2. So here some example for chart models are GPT-4, Claude 3, Gemini, Mistral 7B, Instruct, Phi 2. And for example for embedding models are Text Embedding 3 Large, Embed English version 3.0, BGE small en version 1.5, Sentence Transformer, and so on. Now, the difference between base model LLM or text completion model and chart model are as follows. So here a large language model trained to complete or generate text given a single prompt. A chart model is a conversational AI model specifically designed for multi-turn dialogue. They understand conversation context and can maintain coherent exchange with user. So here we'll give string as input, we'll get string as output. Here we'll give list based messages and we'll give this AI message as output. So this is designed for single shot or one turn completion like summarization, translation, and basic question answering system. Chart model is built for ongoing conversations, instruction following, and interactive dialogue. Now this is trained on large text corpora without specific structure or role context. And chart model is fine-tuned on conversation dataset with roles such as system, user, and AI. So no inherent support for memory. We have native support for chart model. Then there are no role awareness in case of base model. Chart models are fully aware of roles, can distinguish instruction, questions, and replies based on the message type. These are some examples and these are the use cases. So everyone is moving from base LLM model to chart models. So in this video we'll be talking about chart models and embedding models only. So chart models are language models designed to interact through structured role-based messages. These roles are system, user, and AI. LangChain provides wrapper that makes it easy to use them with standardized API. These models are ideal for multi-turn conversations where the model must maintain context, obey system instruction, and respond based on role semantics. So in chart model, we have both closed source model and open source model. These are some examples of closed source model, and these are some examples of open source model. Now, what is a closed source model and what is a open source model? So open source model, these are freely available models that can be run, modified, and fine-tuned locally or in your own cloud. Closed source model, these are proprietary models hosted by companies such as OpenAI, Anthropic, Google, and accessed via API. There are some examples of open source model and there are some examples of closed source model. Now open source model, they are typically free or low cost to use. The cost we may incur cost in case of infrastructure building to maintain and run these open source models. In case of closed source model, the cost will be pay per use. That means based on the token usage, will be incurring cost. Now we have full control over inference behavior, model weights, and customization in case of open source model. While in case of closed source model, we have limited control. Now data privacy, we have high data privacy in case of open source model because we are using our own infrastructure to develop and run, but data is sent to third-party server in case of closed source models. So privacy is a big concern in case of closed source model. Now deployment, we can deploy locally or on a private cloud. This one is deployed via API on providers infrastructure. We have to fine tune, we have to create or modify the open source model according to our custom usage in order to get the optimal performance. But closed source model are optimized for scale, performance, and reliability out of the box. Now let's start with OpenAI models. Now before going further, let's create APIs for OpenAI, Google, Hugging Face, and Anthropic. Now go to this page and click on create new secret key. Here give a name to your secret key and select project as default project and create secret key. So this is the API key created, and I'll copy the key and put it in the .env file. Now to create API for Google or Gemini API, go to this link and click on create API key. The API key will be generated. Now copy and put it in the environment file. Now to get the API key from Anthropic, go to this link and select on get API key. So you need to pay $5 to get the API key from Anthropic. Fill your information and follow the instruction to make the payment and to get the key. When you complete the payment, you will have something like this. Put your key name. I'm putting here test1. You can put anything you like, and then select workspace as default and click on create API key. Now copy the key and put it in the .env file. To create API key from Hugging Face, sign in into your account. Go to this access token option. To create a new one, click on new, create new token and give your token name here, and then click on create token. So in this way you have created the Hugging Face API key. Now copy the key and paste it in the .env file. So after that you will be having something like this in your .env file. Please ensure that you give these particular names. So it should be Google underscore API key, this should be OpenAI underscore API key, this should be Anthropic underscore API key, and this should be Hugging Face Hub underscore access underscore token. So now we have created our API keys. So OpenAI model, to use OpenAI model, we have something like this. From a LangChain OpenAI, import chat OpenAI, and in chat OpenAI we are configuring GPT 3.5 Turbo. And here we have these options. We have temperature, model, max token, top P, and all these options. So temperature is a sampling parameter that controls the randomness or creativity of the model. So if temperature is 0, model is deterministic. That means the model always gives the same answer for the same input. For 0.7, the behavior is balanced. For 1.0, the behavior is creative, and for greater than 1, the behavior is highly random. So the best practice for temperature is, for factual Q&A and documents, use 0.0 to 0.3. For general chatbots, use 0.5 to 0.7. For creative writing, use 0.8 to 1.0, and for brainstorming, use 0.9 to 1.2. Now we have another parameter that is called top K. So top K sampling here, this picks the next token only from top K most probable tokens, then samples uniformly and proportionally from these K tokens. If K is 1, this is greedy decoding. That means chooses the single most likely token. For example, if the K is 50, the model will only consider the 50 most probable tokens at each step. Another parameter we have top P sampling. So top P picks tokens from the smallest possible set of tokens such that the sum of their probability is greater than the P value. This dynamically chooses how many tokens to sample from based on their cumulative probability. For example, if P is 0.9, the model will include tokens until their total probability mass reaches 90%, then sample from this dataset. Now the order of using temperature, top K and top P is, first temperature will be used, then top K will be used, and then top P will be used. Now let's see OpenAI in action. So this is our code. We are using chat OpenAI here. We are using GPT 3.5 Turbo, temperature 0, and we are using this chart. This is the chart prompt template we have here. This is used to save history to txt file. This is to read history from the txt file, and this is the code to run Chainlit application. So to run this, use Chainlit run hi. we are getting the response from OpenAI here. Now tell me about Bagel. As you can see, we are getting this response from the OpenAI. Now next we have Gemini API. To use Gemini API, we have this Chat Google Generative AI from LangChain Google Gen AI, and here we are using Gemini 1.5 Pro. So these are some parameters that are available here. Now let's see this in action. So here we have same thing. Here we are using Chat Google Generative AI from LangChain Google Gen AI, and here we are using Gemini 1.5 Pro. Now if we run this, so now this is working with Gemini API. So here, hi, we are getting the response. Pitbull, we are getting the response. So now this is how we are using Chat Google Generative AI, where we are using Gemini 1.5 Pro model. Now next model we have from Anthropic. So here we have Chat Anthropic, and here we'll be using Claude Sonnet 4 202 50514 model. So here we have Anthropic, and you can see we are importing that and we are using the model here. So 3, so it's working now. Okay, so next we have Hugging Face models. We have two ways to use Hugging Face models. One is to use Hugging Face API, another one is to download and run locally. So to use Hugging Face API, the code would be look like this, and for this case the code is look like this. Let's first see how to use Hugging Face API. So let's clear this thing. Now this is the code. So we are getting the token from Hugging Face, token from .env file, and then we are using that token here, you can see, and then we are using Chat Hugging Face. We are integrating everything into Chat Hugging Face here, and then we are using that model. So let's run this. 4. So hi. So we are getting the response using Hugging Face API. Now let's see how to use Hugging Face locally. So this thing. So to use Hugging Face locally, we are using this code. You can see we are setting up the Hugging Face home. That means the model will be downloaded at this location. Then we are setting up the pipeline, you can see, and then we are integrating everything into Chat Hugging Face, you can see here. Now when you run this, you can see it is loading and it is downloading all required files. Now let's come back to this after the download is completed. So guys, the download is completed. Let's run the code again. So you can see it is checking the GPU. It is slowly loading, and the model is loaded. Let's say hi. So guys, we are like getting random inputs because the model is Tiny Llama. It is not that of a great model, but it is working. So if you want to load any other model, you just have to change the model name here. Now next we have embedding models. Now embedding models convert text into high dimensional vector that captures semantic meaning. These vectors are used for tasks like semantic search, vector database storage, retrieval-augmented generation, or clustering. Here also we have closed source model and open source model. So these are some examples of closed source model and these are some examples of open source model. Now let's see how to use these embedding models in our code. So here, let's clean this. So first we are using OpenAI model. Here let's run this file. So we are using this embedding model, text embedding 3 large from OpenAI, and we are converting this text into vector. Let's print the entire vector. Let's run again. So this is the vector that is generated from this text embedding model. Now let's see how to use Hugging Face embedding model. So clear this thing, Python 7. So this is the embedding vector that is generated from this model. Today we'll be talking about output parsers in LangChain. Now this is our pipeline. We have learned all these components. Now we have this final output. Let's understand how to parse this output into our required format. So output parser in LangChain are crucial components that take the raw string output from a large language model and transform it into a more structured and usable format. For example, this is the raw output from our model, and we use output parsers to transform this kind of text into this. So you can see this is the content. You can see hello there. So we want the content from here. We don't want all this metadata. Hence, using output parser, we can convert this into this. Similarly, this into this format. Now, why do we need output parsers? Now if you ask the question, why do we need output parser? With output parsers, we have structured data extraction, we have data validation, we have improved reliability, we have enhanced user experience, we can easily integrate within a chain. We can design the output parser in such a way that it will output in this format. Also, it should validate that this variable should be a string, this rating should be a float. In this way, we are creating both schema and we are doing the data validation. Now the chain integration thing. Here, if you take this example, this is our first prompt template. We are passing that to a model. We are getting the output from this model, and using this output parser, we are converting the output of this model into a particular format that will be using in template 2. Then we are using that value in model, and then after getting the output from this model, we are using output parser again, and finally we are having the final output for this chain. In this way, we can easily integrate into chain. So these are the benefits of using output parser. Now here we'll be studying string output parser, list output parser, JSON output parser, structured output parser, pydantic output parser, and custom output parser. So string output parser. This output parser returns the raw string output from the LLM. That means if this is the output we are getting from the model, it is taking the content, you can see here, and it is providing that in a string format. Now let's see this string output parser in action. So here you can see this is our string output parser, this is our model, and this is our prompt, you can see here, and then this is our chain. So this is without any parser, and this is with the parser. Now let's run this and see the output. So you can see without the parser, this is the output we are getting from this chain, and when we use the parser, this is the output we are getting. So you can see this is a clean string. Now this is how string output parser works. Now next one is list output parser. This parser is used when you expect the LLM to output a list of items. This list of items often comma separated or new line separated. So this is the output of a model. Using this parser, we are getting a list of item. So here we have this list parser. You can see comma separated list parser, and then we are using that list parser in our chain. You can see here. Let's run this. So you can see here, this is before the parser, and this is the output we are getting, and this is after parser. You can see this is the output we are getting. So another thing you can see here is like before the parser, this is the prompt we are sending to our model. So you can see this is list 5 popular category items. So for category we have introduced programming languages. So our prompt is simple. This is list 5 popular programming languages items. So this is the prompt when we don't have the parser in our pipeline, and this is the prompt we are sending to our model. But when we have the parser in our pipeline, the prompt modified like this. So here we are sending list 5 popular programming languages item, and with that we are sending this extra information also. Your response should be a list of comma separated values. So this is one example. So this is how our model knows how to convert the output in a particular format, and this is how we are getting the output in a list format. Next one, we have JSON output parser. So here this is the free flow text from our model, and we are converting this information into a JSON format. You can see here. This is because after converting into a JSON format, we can use this JSON object. We can integrate this directly into apps, directly into APIs, directly into databases. So let's see this in action. Now here we have JSON output parser. So we are importing the JSON output parser here. You can see now this is the prompt. This is without any parser, and then here we are inserting the JSON output parser. We are using that here. We are getting the format instruction, and then we are using that information in our prompt, and then we are using the JSON output parser here. Now let's run this thing. So when we run this, you can see, so this is the output without JSON output parser. Now after using the JSON output parser, we are getting output like this. You can see this is a JSON format, and we can easily access each component from this JSON object. You can see. So by using get function, we can easily access each item from the JSON object. The issue with JSON output parser is that here we cannot enforce any schema. That means this is the output of the model, and using JSON output parser, we have this is as the output. So you can see this is like movie title is matrix, key themes. Within that we have a list of dictionaries, and for each dictionary we have theme and description keys, and for each of these keys we have values. But what if we want the JSON output to be like this? So movie title, then theme 1, description, theme 2, description. We cannot enforce any schema in JSON output parser. The output solely depend on the model. So to deal with this kind of issue, to enforce a schema, we have something called structured output parser. So with structured output parser, we can enforce a particular schema that we want. Let's see this in action. So here we have structured output parser. First, this is we are importing structured output parser and response schema. Then you can see this is before the structured output parser, and then here we are defining the schema. So we want the output having keys like product name, price, category, rating and feature, and then here we are integrating this schema into our structured output parser, and then we are getting the format instruction from this parser, and we are using that here in our prompt template, and then finally we are using the parser here. So this is how we use structured output parser. Now let's run this code. So here you can see, without the parser, this is the output, and this is the response schema we defined here, and after parser, this is the output. You can see here, and we can access each item just like we are accessing in case of JSON output parser. You can see, so we can access each item using get function. But here, if we focus here, so this is the original prompt before the parser. So if we go here, you can see this is the original prompt. So before parser, original prompt is smartphone, create a product description for a product type. So a product type, we are sending smartphone here. Now this is without the parser, and after the parser, this prompt is modified into this. So create a prompt description for smartphone. With that, this extra information is added to the prompt, and this is how the model understood that we are using structured output parser. Now let's see how structured output parser solve the issue that we have in case of JSON output parser. So here you can see we have JSON output parser here. Now you can see here JSON output parser. Now here we have structured output parser, and if we run this code, you can see here this is after JSON output parser. So if you can see, for we have a key that is key themes, and for this key we have a list of dictionaries, and within each dictionary we have theme, we have description. So we have separate theme and description for each dictionary within key themes. And using structured output parser, you can see this is the output: movie title, the matrix, theme 1, theme 2, theme 3, and for each theme we have a separate description. So this is the schema we enforce using structured output parser. You can see, so according to this we are getting our result. You can see this is how we are able to enforce the schema which we were unable to do in case of JSON output parser. Now the issue with structured output parser is we can enforce the schema, but we cannot validate the data type. For example, this is the output we are getting from the structured output parser. So here all values, movie equal inception, so this is a string, release year 2010, this is also a string, and rating 8.8, this is also a string. But we want this to be an integer and this to be a float. This validation we cannot do in case of structured output parser, and we can solve this issue by using pydantic output parser. So pydantic output parser strictly validates and passes the LLM output into a Python object defined by a pydantic base model, and this provides a robust type checking and data validation. So let's see that. Here we have pydentic output parser. We are importing pydentic output parser. We are importing base model, you can see. So this is how we want our output to be. We want the output to contain name, which is a string, age, which is an integer, occupation, which is a string, and skill, this is a list. So here we are defining our output schema and data type, and then here we are this is like without any this is without any parser. Now here we are enforcing that schema. We are using that schema in our pydentic output parser. Then we are getting the format instruction, and we are using that instruction here in the template, and then we are using the parser here. And if we run this Python 5, so this is the output without any parser. You can see this is a simple prompt that we are using here. And after using this pydentic output parser, our prompt becomes this. You can see extra information we added so that the model will know that this is a pydentic, this schema is enforced by a pydentic output parser, and then this is the output we are getting from our model. You can see. So in this way we can able to enforce both schema and data type. Now let's see how pydentic output parser solve the issue that we have in case of structured output parser, that is how it is able to enforce the schema. So here we are using both so here we are using normal chain without any parser. Then here we are using the structured output parser, and then here we are using the pydentic output parser. So this is the schema that we are using in case of structured output parser, and this is the schema and the data type we are using in case of pydentic output parser. Now let's run this. So you can see this is without any parser. This is with structured output parser. You can see this is a string, this is a string, everything is a string here. With pydentic output parser, you can see this is an integer, this is a float, and this is the string. So you can see this is how we are able to solve the issue of data validation in case of structured output parser. Now the next output parser is custom output parser. So in this way we can design our custom output parser. So here we have our custom output parser. We are using the base output parser class here. We are inheriting from this class, and here our custom output parser is simply making the text converting the text from lowercase to uppercase. You can see, and we are using that custom output parser like this. Now let's run this thing. So when we run this thing, you can see this is without any parser, and this is after the parser, after using this custom output parser. You can see here. Today we'll be talking about memory in LangChain. So this is our pipeline. Here we are giving one input and we are getting one output, but our model should be able to understand the context. It should be able to remember the conversation that we are having with it. It's not a one-shot question answer system. We are having a conversation with our model and it should remember the past conversation. To give this ability, we add a new module that is called memory in our pipeline. Now what is a memory? Memory in LangChain refers to the mechanism that allows a large language model to retain and recall information from previous interaction within a conversation or a series of operations. Without memory, each interaction with an LLM would be stateless and independent, meaning it would have no knowledge of prior turns or context. Memory enables the LLM to maintain continuity, understand the ongoing conversation, and generate more relevant and coherent response based on the past exchanges. So if you take this example, here we are saying I want to book a flight to London. So chatbot will reply, great, when would you like to depart? Next, when we give this input, next month around the 15th, if we don't have any memory integrated in our pipeline, the chatbot has no knowledge of the destination. So it will get confused and it will give something random. If we integrate memory in our pipeline, it has the information regarding London. So after this, it will give relevant answer, or it will generate relevant text. Now, why do we need memory? We need memory in LangChain for several crucial reasons, such as contextual understanding. It allows the LLM to understand the full context of a conversation, not just the current turn, but the full context and full conversation. This is essential for natural and fluid interaction. Second thing, we have coherence and continuity. Memory helps maintain a coherent dialogue, preventing the LLM from repeating information or asking for details it has already been given. And it helps in personalization. So by remembering the user preferences or past actions, memory enables more personalized and tailored responses. And we have statefulness. Then for applications that require maintaining a state, such as multi-turn forms, sequential tasks, memory is indispensable. Now it reduces redundancy, so it avoids the need for users to repeatedly provide information and improving the user experience. Now in this video, we'll be talking about conversation buffer memory, conversation buffer window memory, conversation summary memory, conversation summary buffer memory, conversation entity memory, vector store retriever memory, conversation KG memory. KG stands for knowledge graph memory. Now what is a conversation buffer memory? A conversation buffer memory is the simplest form of memory in LangChain. It stores all raw messages from the current conversation in a buffer. When the memory is loaded, it provides the full list of these past messages to the LLM as part of the prompt. So let's see this in action. So here you can see we have our LLM and this is our prompt, and we have the placeholder to put the history inside this prompt, and then we are using conversation buffer memory. So if we run this code, so this is our chatbot is live now. Now hi Beagle, then let's say Pitbull, Doberman, so you can see it is remembering all the chat, all the conversation that we are having with it, you can see, and it is providing everything in the prompt. So this is how a conversation buffer memory works. But here you saw that it stores all messages. For longer conversation, the chat history list can be very large. So this leads to exceeding the LLM context window, because we are saving everything in the memory, and we are retrieving everything and putting it into the prompt during our conversation. So it might exceed the LLM context window. Here we are dealing with a large volume of data, so this will increase cost of the operation. Also, this leads to slower responses. To solve these kind of issues, we have conversation buffer window memory. So conversation buffer window memory is a type of memory in LangChain that maintains a sliding window for the last k interactions. Instead of storing the entire conversation history, it only keeps the most recent k exchanges. When the memory is loaded, it provides only this k recent interaction to the LLM. So here we have a sliding window of k interactions of size k. So here, as you see, we are dealing with a smaller volume of data, hence it is faster in inference it incurs low cost. Hence, it solves the issue with the conversation buffer memory system. Now, let's see this in action. So here we have conversation buffer window memory, and we are taking k equal to 3. So hence we will be storing only 3 number of conversation. Now let's run this. So now let's run hi, again pitbull, beagle, then so if you can see, it remembers only last 3 conversations. So this is because of k equal to 3, and this is how conversation buffer window memory works. Now here we have some issues with this kind of memory. Here, as we are losing some information, we might lose some important information that happens beyond this k number of interaction. Now the next type of memory we have is conversation summary memory. So conversation summary memory is a more advanced type of memory in LangChain that uses an additional language model to create a concise ongoing summary of the conversation. Instead of storing raw messages or a fixed window of messages, it continuously updates a summary of the dialogue. When the memory is loaded, it provides this summary along with the very last few raw interaction to the main LLM. So here we are not sliding a window, we are not keeping the raw text just like we are doing in the previous case. So here we are taking another LLM call to create a summary of the conversation, ongoing conversation, and we keep that in our memory. While dealing with a new conversation, we take this summary with the user query and give that to LLM. Now let's see this in action. So clear. Now this is our conversation summary memory. So here we are using the LLM to create the summary, and this is the chart history. This is the memory key because we are using same key here to put the history in our prompt, and then this rest of the thing is the same. So here if we see, okay, let's run this code now. Chainlit run 3. So here hi, beagle, pitbull, Doberman. So you can see here it is creating a summary of the conversation. It is not taking a sliding window or taking the raw messages. It is creating a summary and appending and putting that into the prompt. You can see here. So this is how conversation summary memory works. Now in this case we are also not dealing with a large amount of data. We have a summary that is good. We are dealing with a smaller amount of data as compared to the previous models. We are not losing any crucial information because we are creating the summary. But here we are doing additional LLM calls, and that will incur cost. That will also feed to the latency. That means we'll have high latency using this extra LLM calls. Here the summarization quality is dependent on the LLM. So the LLM might give poor quality summary, hence we might lose some information. Also the LLM might hallucinate in the summary. These are some limitations of this kind of memory. Now next we have conversation summary buffer memory. So conversation summary buffer memory is a hybrid memory type in LangChain that combines the strength of conversation buffer window memory and conversation summary memory. It maintains a buffer of recent raw messages up to a certain token limits, and beyond that limit it uses an additional LLM to summarize older messages into a concise ongoing summary. When loaded, it provides the LLM with the latest raw messages and the accumulated summary of the older conversation. Now let's see this in action. So let's go this. Here we have conversation summary buffer memory. So here we have a maximum token limit, that is 150, while using the LLM to create summary. So beyond this token limit, it is creating the summary and keeping that in the memory. And then while dealing with a new conversation, it is feeding that summary with the new conversation and certain conversation that is within this token limit to the model. So let's run this. So hi Beagle, you can see it is creating the summary, and then it is having some recent conversation, you can see here. So in this way it is creating a sliding window, as well as it is creating a web summary of the previous or past conversation. Now, so here we have the benefits of sliding a window, we have the benefits of creating the summary, but here also we are taking an additional LLM call, and that leads to higher cost and higher latency. Also we are dependent on the LLM to create a summary. The quality of the summary may be poor, LLM may hallucinate. It is very complex to integrate this memory in our pipeline. Now next type of memory we have is conversation entity memory. Conversation entity memory is an advanced memory type in LangChain that focuses on extracting and tracking information about specific entities mentioned throughout a conversation. Instead of storing raw messages or summary of turns, it maintains a dynamic, evolving knowledge base of entities and their associated properties as inferred from the dialogue. When loaded, it provides the LLM with the entity information relevant to the current query, along with the most recent conversational turns. So basically here we are not doing any summarization, we are not sliding a window. Here we are detecting important entities and we are storing all the information related to those entities. So let's see this in action. Here we have this, so conversation entity memory, and we are using LLM to find the entity and their relevant properties from our conversation. So if we run this, now I have a dog, its name is Tommy. Tommy likes ice cream. So you can see here it is storing the information related to Tommy. So it identifies Tommy as an entity, and it is remembering all properties related to Tommy. So if I ask this question, what is the name of my dog, you can see it is giving the perfect answer. So it is not creating summarization text, it is not using any kind of sliding window. It has identified the entity, that is Tommy, and it has stored all relevant information related to Tommy. This is how conversation entity memory works. But here also we are doing an additional LLM call that incurs higher cost, higher latency. The entity extraction quality is dependent on the LLM. So definition of entity may is a vague idea in this case. So LLM, the entity that we want might be different from whatever LLM is giving to us. The complexity of implementation of this kind of system in our pipeline is high. So these are some limitations with this kind of memory. Now next we have vector store retrieval memory. Vector store retrieval memory is an advanced memory type in LangChain that utilizes a vector database and a retriever to manage and access long-term conversational history or external knowledge. Instead of storing raw messages directly in the memory or summarizing them, it converts past interactions into numerical vector embeddings and stores these embeddings in a vector database. And when, for a given user query, retrieves the most semantically relevant chunks of information from the database, then these retrieved chunks are then provided as context to the language models. So here we are converting the past interaction into embeddings and we are storing them in a database, and while the new conversation we are retrieving relevant information from the database and giving that to our LLM. So here we have, you can see, so we have, this is our prompt. So these are some past information that we are going to store in this ChromaDB, and then we are using retriever. You can see as vector store retriever memory, we are using the retriever here, and memory key is retrieved history. Here we are using the same key. So basically these are the conversations that we store in the vector DB, and then while accessing while doing a new conversation we can access important information. Let's run this thing. Chainlit run 6. So here we have information regarding Max, and here Whiskers we have information regarding a dog and cat. So if I ask the question, what is my dog's name, you can see we are getting relevant information and correct information. Your dog name is Max, a golden retriever, you can see here. So this is how vector store retriever memory works. But here the issue is like we are depending on the type of or the quality of embedding. We are doing these extra calls to create embeddings, store embeddings, or retrieve the particular embeddings from database. So all these things incur cost and it increases the latency. Here also this is not a simple solution. This is also a complex setup, and we need to be very careful while applying this kind of setup in our pipeline. Next we have conversation KG memory. Conversation KG memory or knowledge graph memory is an advanced memory type in LangChain that explicitly constructs and maintains a knowledge graph based on the ongoing conversation. It uses an additional LLM to identify entities and the relationship between them from the dialogue. So this structured knowledge graph is then used to provide highly precise and relevant context to the main LLM, so allowing for deeper and consistent factual recall even over very long and complex conversations. So basically here we are not using any kind of memory that we learned previously. Here we are identifying entities and we are creating a knowledge graph. We are creating a knowledge graph between them. So in this way we have the relevant information, we have the idea, but we are taking a very smaller space, or we are working with a very smaller volume of data. Now here we have this knowledge graph memory, you can see. So this is our LLM, this is the prompt, this is our conversation KG memory, and we are using LLM to identify entities and to create the knowledge graph. So if we run this thing, 7, so hi, I have a dog, my Dog's name is Max. He is a beagle. He is white. So if you see here, you can see it has identified Max as an entity. Then it is appending the properties to Max. You can see Max is a beagle. Now here Max is a beagle, Max is a white. So it is creating the graph slowly, and in this way it is extracting the relevant information without storing a large volume of data. And this is how conversation KG memory works. So the issue with this kind of memory is we are doing an external LLM call that incurs high cost, that increases latency, the knowledge graph extraction quality, the entity identification quality, they both are solely dependent on the LLM. So LLM might hallucinate, LLM might create poor quality, might extract poor quality entity or poor quality knowledge graph. It is very complex to integrate in our system. So there are some limitations of conversation KG memory. Today we'll be talking about RAG in LangChain. To understand RAG, let's first understand how the models are trained. To train a model, we collect data up to a certain date and then we train the model on this data. So this date becomes knowledge cutoff date. Every model has a knowledge cutoff date, as you can see here. So the model will get confused if we ask about certain event that happened after 1/1/2025, because this is our knowledge cutoff date. If we ask about private domain specific data, because this is not available on the internet, the model may hallucinate and give random answer. The model would unable to explain the source of its answer. Now, to solve this thing, we have fine tuning, we have pre-training with new data, we have few short learning. Now fine tuning, continue training an existing model or LLM on a smaller domain specific data set to adapt it to your needs. So basically we collect new data set and then we'll fine tune the model on this data set. So some pros of this approach is that it specializes the model on your domain on this collected data set. It reduces hallucination within that domain. It improves the performance on repeated predictable tasks. But the issues with this approach is it is expensive and time consuming because it needs GPU and data curation. It becomes static, doesn't dynamically update with new knowledge, because to update with new knowledge we have to collect the data again, we have to train the model again. Still struggle to cite sources, can forget general knowledge if over fine-tuned, or the issue of catastrophic forgetting. Second approach is pre-training with new data. We can retrain or continue training the entire model from scratch with an expanded updated corpus. So the pros are broadly updates the model's core knowledge because we are creating the model again and again from scratch, ingest huge amount of fresh data including new events or domains. The issue with this approach is it is extremely resource intensive. We need hundreds of GPUs and weeks for training. Cannot be easily done by most organizations because to train the model from scratch is a very sophisticated task. Still a black box, no citation, cannot point to exact source. Also, once trained, the knowledge is again static. So we are not dynamically updating the knowledge. It has the same issue because we are training the model again, then we have a knowledge cutoff date. Now the third method is few short learning. Providing a few level examples in the prompt to teach the model how to respond correctly in the current conversation. So this is the prompt. You can see we have some examples with the question and then we are asking the question. So these are some advantages, such as this is cheap and easy to integrate. This is flexible, fast to experiment. No infrastructure required. We can work with the existing infrastructure. But the issues with this approach is this is limited by the context window size, because every LLM has a token limit or context window size. We don't know how many examples should we give to get a proper answer. Still cannot give the source. Now to solve all these issues, we have RAG. Now using RAG, instead of hardwiring domain knowledge, RAG stores it in a retrieval index that is easy to update anytime. No need to retrain the LLM to incorporate new knowledge. Dynamically grounds answer from retrieved documents, so you get traceable sources. It keeps general reasoning ability of the base model while letting retriever handle domain knowledge. So we are not changing the base model, we are using the base model as it is, and we are using a retrieval to handle the domain knowledge. So we can create different RAG applications based on different domains. RAG uses a retriever to automatically pick relevant example or knowledge from vast corpora. It injects only the relevant context into the LLM prompt by passing token limits. So it is not giving the entire thing. It is finding the relevant thing and it is giving that into the prompt to LLM. Now it dynamically scales to massive knowledge bases without manual prompt stopping. So we use vector databases, and we can update the vector databases based on the latest knowledge, and RAG can retrieve all those knowledge automatically or dynamically. It can always link the retrieve sources for explainability. So these are the benefits we are getting by using RAG. Now this system that we saw in the previous video, this is a RAG. So RAG stands for Retrieval-Augmented Generation. So basically we can have different sources. You can see, so this is our PDF, this is the internet, this is a private database. So we have different sources. We can load the data, we can do the splitting, we can save that in a vector database, we can use retriever to retrieve relevant document, we can add that information in the prompt, and we can give the prompt to LLM and will give our final output. Now you can see this retrieval comes from retrieving the relevant document. This augmented comes from augmenting the relevant document with the user query, and this generation comes from the generation of our required answer. Now with this system we are reducing hallucination. We are not dealing with the headache of training or fine tuning the model, and we are getting proper answer. Now in this video we are going to build this entire system. So this is our code. So here we have data, we have scripts, this is gitignore file, this is compose file for local development, this is for production, this is docker file, this is readme, and this is requirement.txt, and this is .git folder, and these will be created when we run the code. And within scripts we have main.py, and then within utils we have all the required Python files. Now let's go with the flow to understand the entire thing. So here you can see this is the docker compose file. Image name will be RAG models, the container name will be Luna, and then we are exposing port 8000. That means our application will be running on this port, and here we are mounting different volumes. Then we are changing the work directory to scripts, and within this directory we are running this command. So here we are running the chain lead application, and we are running that at 8000 port. Now let's check the main file. So here we are loading everything from .env file. We are setting up the logger here, and then this function is responsible for initializing everything that are relevant, that are required before starting the chain lead service. So first, this is Luna config. Here we are setting up directories. If we go to this code, you can see we have directories here, we have model information here, chunk size, chunk overlap, we have memory window, top k, then max response words. Then this is the method we are using, you can see. So here we are creating all the required directories if the directories are not present. Then after that, this is the Luna RAG. This is our AI, you can see. So we are first setting up Chroma Manager. So Chroma Manager is responsible for dealing with Chroma DB. You can see this is our embedding model, and then this function is responsible for creating vector store, you can see. Now this function is responsible for loading the vector store if it is already available, and then this is to get the retriever, you can see. Next we have chart history manager. So this class is responsible to manage history. You can see this is to get the txt file, because we are saving history like this. So here you can see in chart history we are creating a txt file with respect to session id, and then we are saving history like this. And then here we have the vector database. Then here we save logs like this, you can see. And then here we have the PDF. So we are using this PDF to create the vector database. Now after that, here we have greeting handler. So we are not running the entire RAG pipeline if the user sends any greetings. So we are detecting whether the message is a greeting or not using these regex expressions, you can see. And then we give an appropriate answer from these available answers. So for greeting messages, we are detecting the message and we are giving the answer. We are not running the entire RAG pipeline. Now this function is responsible for doing that checking, that greeting checking, and this function is responsible for giving the appropriate answer. Now after that here we are creating our LLM, you can see here. Then we are initializing all these functions. So after initializing our Luna class, we are calling the initialize system. So here this is the function we are calling here. We are loading up, or we are checking up OpenAI key in the environment. Then here we are checking if vector database is available or not. If the vector database is available, we are loading from the existing database. Otherwise we are creating a new vector database. So for that we are calling this PDF processor. So this class is responsible for dealing with PDFs. You can see we are creating the text splitter here. This function is to load PDFs. You can see using directory loader we are loading PDFs from a directory. Then here you can see, so here this function is responsible to create to do text splitting, you can see. Now here you can see first we are loading all PDFs, then we are splitting the documents, and we are creating the vector store. Then after that, this is our prompt, you can see here. So we are using this prompt to create the prompt template. And then after that, this is the conversation buffer window memory we are using as memory. Then this is the chain, this is the LLM chain. You can see we are using LLM, retriever, memory and prompt. Now after this, the system is initialized and ready to be used. So here the system is ready to chart now. After that, here we are calling this function. So this function is to create this art in the logs or in the terminal. So remember, this is the log file. So this function is responsible to create this art. Now after creating the dart, so in this way we know the system has started. We initialize all the required LLMs. Here we are calling this function here. Then after that, here this is when the chain lead starts. When the chain lead starts, we first check whether we have initialized Luna RAG or not. If the model is not initialized, then we are trying to initialize here, you can see. Then after that, we are getting the session ID. We are showing we are loading history with respect to that session ID if available. Then we are showing this greeting message on the chart. You will see how it looks on the chart. Then this is when the chain lead starts, and this is when we receive one message from the user. So when we receive message from the user, you can see we are getting the session ID. We are checking whether Luna rack is initialized or not. We are checking whether, then here we are sending that message. We are calling this function, you can see. So here we are getting the question, we are getting the session ID, and with respect to that we are checking whether the question is a greeting or not. If it is a greeting, we are getting the appropriate answer using this function. We have already seen this function. Then we are saving that in the txt file with the tag user or AI. Then here we are adding the messages and response to the memory, and then we are returning the greeting response with the tag greeting. Now if it is other than any greeting messages, then here we are running the LLM chain, the entire RAG pipeline, and then we are getting the response, you can see here. Then these are for logs, and we are saving the chart history in txt file using user or AI tag, you can see. Now this is after getting the answer, we are displaying on the chart platform. Now this is when the chart ends, we are logging this with respect to the session ID. So this is the entire RAG system. Now let's run this system. So here, now to run this, type docker compose -f of d. So if the docker image is not available, you can see it will create a docker image like this, and it will start the container. Now before starting that, let's delete everything. Let's delete chart history, this vector database, then logs. So we have deleted everything. Now let's run the code. So here docker images. So I have already created the images, you can see here. I don't have to recreate the image even. But if when you run this code, it will create the image and it will start the container. So it has started the container. Now let's see the logs. Docker logs. Okay, before that let's see the container. You can see this is the image name and this is the container name, and we are exposing the model. We are running the application at 8000 port. So let's check the logs. You can see it has created this art that we have discussed. Then it has initialized everything. It has created, you can see it has created the ChromaDB vector database. Then it has initialized the Luna rack system, and the application is live at this port. So if we go to localhost 8000, you can see this is the welcome message we are getting. So if you check that with code here, okay, just a second. So here you can see this is the welcoming message. Our application is live now. Let's start a conversation. So hi, you can see, so greeting detected, and it has given a response. Now let's type bagel. So you can see it is here. After conversation 1, this is conversation 2. So entering into LLM chain, then this is the chart history, and then here you can see entering into new LLM chain, and this is context from the document. You can see all this information it has retrieved from the document. Now you can see here we have integrated chart history inside the prompt, and we are sending this to our LLM, and then finally we are getting this response. You can see. Now let's type pitbull. And this is the prompt after integrating chart history and relevant documents. You can see here, and then you can see we are getting the final response here. So similarly, let's type height of beagle. The entire process happened here, and then we are getting the response. If you type color of pitbull, so we are getting proper answer from our system. So guys, if you go to data and chart history, you can see the file is created with a session ID name, and then we are storing everything in this txt file. Then if you go to ChromaDB, we have created the required vector database here. Then if you go to logs, we have the entire log here. You can see. So guys, we have created our RAG system, and we have created this entire pipeline, and we have created videos for each component in this series. So I would suggest go learn about each component from those videos. It will be very helpful to build this application. Today we'll be talking about runnables and chains in LangChain. Now what is a runnable? At its absolute core, a runnable in LangChain is just anything that can be executed in a standardized way. Think of it as a function that always has the same calling conventions. For example, every runnable is designed to have these core abilities. We have invoke. If you give it one input, it will give you one output. This is like calling a regular function. We have batch. If you give a list of input, it will efficiently process all of them to give you a list of output. And we have stream. If you give it one input, and it starts sending you chunk of output over time as they become available. So this is crucial for responsiveness in AI. Let's take an example to understand runnable. So this is the code that here we are saying tell me about a topic. We'll give one topic to this prompt, and it will then it will format the prompt. That means it is creating the prompt using the topic that is AI here, and then it is after formatting the prompt, we are using that to do the predict function. So see here, for this prompt component we have dot format, and for LLM we have dot predict to use these components. Now with runnables we can convert this into something like this. So for prompt we have invoke, for results for LLMs we have also invoke. So similar calling conventions we are using here. If we use chains, this code becomes something like this. So we are combining everything into a chain, and we are using dot invoke. So when we combine multiple runnables, it becomes a runnable also. So in this way you can see it's very easy to integrate everything together to create complex chains, to use the similar conventions while we are building a complex LangChain model. Now if you can see here, we have this is one component, this is one component, this is the third one, Then after creating the embedding, we have this retriever component, then we have this prompt component, LLM component, and output parser component. So it is very easy to build this kind of complex system because of runnables. So output of one component becomes input of another component automatically. Now what is a chain? So in LangChain, a chain is a sequence of calls to different components where the output of one component serves as the input to next, and allowing you to combine multiple operations to achieve a more complex task. Think of it as a pipeline or workflow for your language model application. Instead of performing each step manually and passing data between them, a chain automates this process. So if you look at this example here, this is one component, this is the second component, and this is the third component. So here we have seen this example earlier. You can see without chains we need to write code like this. We need to deal with each component manually, and with chains this entire thing becomes a single line, and then we are using that chain to do the invoking here. This format of using pipe operator to create chains is known as LangChain Expression Language, or LCEL. Now here we'll be talking about runnable sequence, runnable parallel, runnable pass-through, runnable lambda, and runnable branch. Now what is a runnable sequence? Runnable sequence is a core component in LangChain's expression language that allows you to chain multiple runnables together in a specific linear order. The fundamental idea is that the output of one runnable automatically becomes the input for the next runnable in the sequence. So let's take this sequence. So here we have prompt template, then that output of this component goes to chat OpenAI, and then output of this component goes to string output parser, and then we are finally getting the output. So this is a linear order chain. Now if we check the code, so here you can see this is our chain. So this is prompt, this is LLM, and this is parser. So here this is our prompt: generate a short creative name for a product type called product name, right? So we have two inputs, and here we are giving these two inputs to our chain. You can see, so we are invoking the chain here. Here we are describing the chain, and here we are invoking the chain. And if we run this Python 1, you can see generated them beautiful mornings. You can see here. Now next we have runnable parallel. So runnable parallel is a key component in LangChain's expression language that allows you to execute multiple runnable concurrently or in parallel. Unlike runnable sequence where the output flow linearly, runnable parallel takes a single input and passes it to all its contained runnable simultaneously. So basically we have the input, we have two runnable chains here. You can see we have two runnable components. Using runnable parallel, we pass the input to both of the components simultaneously, and they process the input, and then they give the output respectively. So here what we are doing, for this component or this chain is responsible for create a summary, and this chain is responsible for extracting keywords. They both receive the same text here. Now let's see this in action. So here this is our LLM, this is our first prompt, this is the prompt to create summary, and this is the prompt to extract keywords. Now this is our first linear chain, this is our second linear chain. This is responsible for summary, and this is responsible for keyword extraction. And using runnable parallel, we can use both chains simultaneously. So this is the text we are giving to both of these chains, and then when we do this invoking, it will give the results automatically. So clear Python 2. You can see, so we have given the text, and here you can see we have summary and we have keyword extracted. So both chain ran parallelly and gave this output. Now next we have runnable pass-through. So runnable pass-through is a versatile runnable in LangChain's expression language that primarily serve two main purposes. First one is identity function. That means whatever input it receives, it returns the exact input as its output unchanged. And the second one is input manipulation with .assign function. Its most powerful feature is the .assign method. This allows you to add new keys to a dictionary input, modify existing key in a dictionary input. So basically we have this pipeline. When here we are doing like we are creating a summary on a particular topic, then we are creating caption on top of this summary. So but at the end of this pipeline, we need both summary and the created caption. So summary is created from the input text and caption is created from the summary, but at the end we need both summary and the created caption. Hence we are creating the summary first. We are giving that as input to both of these runnables. So this runnable is creating the caption, and this is a runnable pass through. This is simply receiving the summary and passing that to the next level unchanged. And in this way, at the end we have both summary and our created caption. Similarly, here we receive the input using runnable pass-through.assign. What we are doing here is, if the topic is cat, add the adjective key that is hilarious. If it is other than cat, add the adjective key that is thrilling. And in topic we have the text, we have the topic, and in adjective we have the text either hilarious or thrilling based on this condition. And then we'll pass that to runnable sequence and get the output. So here we are just passing the input as it is without any changes, but here we are changing the input based on a condition. Now let's see this in action. So here you can see this is write a short summary about a topic. This is write a catchy caption for this summary. So this is the input for this template would be the summary. Now here what we are doing, we are creating the runnable sequence first to create the summary. Using this parallel chain we are doing both pass through thing and we are creating the caption, and we are combining everything together. So here summary generation, first we are generating the summary. Remember, first we are generating the summary. Now using the parallel into the parallel chain we are passing through the summary, and then we are creating the caption. And when we run this, you can see this is the final result. We have the summary and we have the catchy caption here. Now the second type, here you can see this thing, we are building this thing. So the prompt will be write a, this is one key, that is adjective short story about topic in 50 words. So if we give the topic as cat, the adjective becomes hilarious. If the topic is anything but cat, the adjective becomes thrilling. So this is the condition we are writing here, you can see, and this is our runnable pass through, and we are using .assign method. So when we run this, you can see we have run the code. So here if first input is cats, you can see, hence the prompt will become like write a hilarious short story about cats in 50 words, and here we have the short story. And when the topic is space exploration, the prompt becomes write a thrilling short story about space exploration in 50 words, and based on that we have this output. Now this is how runnable pass-through works. Now next we have runnable lambda. So runnable lambda is a versatile runnable in LangChain's expression language that allows you to wrap any standard Python function or lambda expression and make it compatible with the runnable interface. So basically, if we have a Python function or lambda expression, we can use runnable lambda to convert that into a runnable. So basically, if let's say we have a function, Python function, that asks greeting to an input. So if the input is Bob, the output of the function would be hello Bob. So we convert that function into a runnable using runnable lambda, and then we use that in the pipeline. So here you can see we have this this function is to do uppercase, and this function is to add greetings. So here we are creating two runnables here using runnable lambda, and then here this is we are using the uppercase runnable to convert this input into uppercase, and then here you can see we are using that greetings runnable, you can see here in the pipeline. So this is a pipeline we have created, and we are using that in this pipeline. So let's run this. So you can see first this is the input, and we are using runnable lambda. We have converted the input into uppercases, you can see. Now here you can see first we are using greetings runnable. So this outputs hello Bob, you can see. Now we are using this output into this entire pipeline, and we are getting this this message as a final output from this entire pipeline. Now this is how runnable lambda works. Next we have runnable branch. So runnable branch is a powerful component in LangChain's expression language that enables conditional routing within your chains. It allows you to direct the flow of the data to different runnables based on specific conditions. So it's like an if, elif, and else statement. We have these many runnables and these many conditions. So if the intention is greeting, we'll run this runnable. If the intention is math, we'll run this runnable. If the intention is farewell, we run this runnable, and if it is a default, then we run the general QA chain runnable. Now based on this intention, we divert the data flow into that particular runnable, and after that we'll get the final output. So here you can see this is math solver runnable chain, this is general question answer chain, this is greeting chain, this is farewell chain. So we have 4 different conditions, and we created this function to identify which conditions we are working with. Now this is runnable branch. So we are using runnable lambda here. So for if the condition is greeting, we are using greeting runnable. If the condition is math, we are using math runnable. If the condition is farewell, we are using farewell runnable. Else we are using general question answer chain. So you can see this is a if, this is elif, this is elif, and at the end we have else condition. And we have these scenarios. First this is hello, this is a greeting case, this condition is for math, this is a general question answering, this is a farewell case, and this is also a general question answering case. Now if we run this code, you can see, so for each case we are running as a particular runnable chain here. Today we'll be talking about tools and tool calling. So what are tools in LangChain? Generally, LLMs are excellent at generating text, understanding context, and reasoning, but they do have limitations. They lack of real-time information because LLM's knowledge is limited to their training data. They don't have any ability to perform any kind of action. They cannot send emails, they cannot query database, they cannot run code, or they cannot interact with any kind of services. They also have limited computational abilities. That means we cannot use LLMs for precise calculations or complex logical operations. To give these kind of abilities to LLM, we have tools. So a tool is essentially a function or an API that a large language model can use to interact with the outside world or perform specific defined actions. So basically, with the help of tool, LLM can perform actions. And what is tool calling then? So tool calling is the mechanism by which an LLM decides that it needs to use a tool, it determines which tool to use, it specifies the argument for that tool. So basically the pipeline looks like this. First we'll bind the tool to our LLM. Then after receiving the user query, it decides whether it should call a tool or not. If a tool call detected, the tool is getting executed and the result of this tool call along with the user query is given to the LLM, and then LLM generate the final answer. And this is the pipeline, and this entire thing is called tool calling. Now typically a tool has a name, a description and an arguments. So name is name of the tool, description is description of what it does, and arguments are the parameters that the tool expects. So if we take DuckDuck search as an example, we have this name equal to DuckDuckGo _ search, description a wrapper around DuckDuckGo search useful for when you need to answer questions about current events. Input should be a search query, and required for arguments we have query, the descriptions like search query to look up. Now let's see DuckDuckGo in action. So here this is our LLM and this is our DuckDuck search run tool that we'll be using. So when we do search tool.name, we'll having the name of this tool. This is for getting the description and this is for getting the arguments. Now here we are binding this tool to our LLM, you can see. Then in this function we are first getting the user query, and then we are appending that as a human message to our messages. Then we are invoking the LLM here, you can see. Here LLM decides whether to call a tool or not. So if a tool call is detected, you can see we are getting that tool call from the LLM response. Then we are invoking the tool accordingly. Then we are appending the tool result back to the messages, and then finally we are sending the entire messages here. So here this is our final LLM call and we'll be getting our final result. Now let's run this code. So here the question is, what is the latest news on India? You can see we have name, description and arguments. Then this is our user query, and then here you can see we are finally tool call is detected, then it is doing the tool execution, and finally this is the entire thing that this is the final message. This message we are sending to LLM, and after that we are having the latest information. So this is how we define our tool and we perform tool calling. Now if you want to learn about other tools, you can go to this link. So here we have a number of tools, you can see, within different categories. So if you want to use any tool, you can use from here. Now let's understand how to build a custom tool. So we'll be using tool decorator, structure tool plus bidenting and base tool. So let's understand how to use tool decorator to build a custom tool. So this is the function. Here we are adding two numbers. So here first we'll be using tool decorator, then here we are using type hints, that is we are ensuring, we are mentioning like what is the type of inputs and output. Then you can see this will become the tool name, and then we are using the duck string to add the description. Remember, we have the description from our tool. By using duck string we can add description to our tool, and then we have this return function. So when we do tool.name, it will say the name of the tool will be our number, and for description it will give this answer. Now this is the function we wrote in Python, right? But what does LLM see when we give this function to it? So when we give this function to LLM sees something like this. So description are two floating point number, the description we have here, then properties here, then required A and B, and title add number. So this will be the name of the tool. Now let's see this in action. So here we have defined our tool using tool decorator, and we are extracting different information from our tool here. We are binding the tool to our LLM, then we are calling the tool here. So here we are doing the same thing again. We are getting the user input, then we are saving that as human message to our in our messages. Then here we are invoking the LLM. Here LLM decides whether to call or not call the tool, and then if the tool call is detected, here we are executing the tool. Here we are getting the tool call from our LLM response, and then here we are executing the tool and adding the result to our messages, and finally we are getting the result from here. Now let's run this thing. So when we run this code, you can see the name is add numbers, description, this is the description we have given in our tool, you can see, and then arguments, we have these arguments in our tool, and then this is what the LLM sees. So then here you can see this is the user query, this is the response from the LLM, and here if you see we have tool calls detected, name is add numbers, these are the arguments, then we have an unique ID for this tool, and then here the tool is getting executed, and then finally we have our answer. So in this way we are able to create a custom tool using a tool decorator. Now let's see how to create a custom tool using structured tool and pydantic. So here first we define the schema using pydantic schema and the type of the input variables. Here you can see we have both the variables as float, and then here this is the function we define. This is the function that will take two variables and that will add them and give the final output. And then using structural tool we combine everything together, you can see. So we are giving the name here, this is the description, and this is the schema. Now let's see. So here we have structured tool, this is our LLM, this is the schema using pydantic, and this is the function that we are going to use, and here we are combining everything to create our custom tool. And if we run this, so same thing here, everything is getting executed and we are getting our final answer, you can see here. Now let's understand how to create the tool using base tool and pydantic. Similarly, we are defining the schema using pydantic here, then we are using the base tool, and then you are creating this class. So here we are using this pydantic schema, you can see, and then we have the function here. Now when we run this, when we use this tool, we'll be able to do the addition. So here you can see we have pydantic schema and LLM here, then this is our base tool using base tool, we have created the tool, and we are creating the instance of this class, you can see, and then we are using that class. We are binding to our LLM, and then the rest of the pipeline is same. So Python 4, you can see. So after going through the pipeline, we are finally getting the answer. Today we'll be talking about agents in LangChain. An AI agent is a sophisticated AI system that goes beyond the basic functionality of a traditional large language model to perform tasks autonomously. Instead of simply generating a response to a single prompt, an AI agent is designed to have a goal, create a plan to achieve that goal, and then take action in real world using a variety of tools. AI agent is autonomous. It can take a high level request and execute a series of actions to fulfill it. For example, if you ask the agent, find a flight from New York to London for next month, get the cheapest price, and send me an email with the details. Now, instead of needing further instruction, the agent autonomously checks a calendar for next month's date, searches multiple flight booking websites, compare the prices it finds, drafts an email with the flight information, and send that email to you. So it will perform all of this without you having to guide it through each individual step. Now, so the AI agent reasons by breaking a complex task into a logical plan and then adjust that plan as needed. So if the goal is here, help me plan a weekend trip to a new city. So it will decompose this request into further actions. So find a city that I have never been to, find a hotel in that city, find activities to do there, and create a simple itinerary. So after decomposing the tasks into these smaller tasks, it starts planning. The agent creates a step-by-step plan. Access my past travel history, uses a web search to find a list of popular weekend destinations, compare the list to travel history to find a new city, search for hotel and activity options for that city, compile information into a proposed itinerary. Now the third property is it uses tools. An agent uses external tools to expand its capabilities beyond its internal knowledge. So here the goal is what's the weather like in New York tomorrow, and how will it affect my commute. So the agent uses a weather API to get tomorrow's forecast for New York. It then uses a mapping API to calculate your typical commute time. Using its reasoning, it combines the weather and the commute date to predict potential delays and suggest alternative routes, providing a detailed and actionable response. So an agent has different kind of tools, and it is able to use appropriate tools to perform appropriate tasks. And then agent has memory. So memory allows the agent to maintain context and learn from the past interaction to provide a more personalized and consistent experience. So agent has short-term memory and agent has long-term memory. Then an AI agent is adaptive. So adaptivity is an AI agent's ability to adjust its plan and behavior in real time based on a new information and unexpected events. So for example, if our goal is to plan a flight and hotel for a weekend trip to a new city, but I have a budget of $1,000 for everything. So initial plan is to the agent uses its tools to search for flights, hotels, aiming to stay within the budget. So but here let's say agent finds a clear flight for 300 and a hotel for 750. But here the issue is the entire cost will be 1050, which is over the user's $1,000 budget. Now the agent will adapt to this condition. So instead of simply saying I can't meet your budget, the agent adapts to its plan. It uses its reasoning and understands that the hotel is the problem. It then initiate a new plan, search for a cheaper hotel that fits within the remaining $700 budget. If that fails, it might expand its search to include hotel slightly farther from the city center, or suggest a different travel date. it can then present a new valid option that fits user's original budget. Now to create an agent, we have different design patterns, and if you go to this link, you can get a lot different design patterns that are available. You can see here. Here we'll be using this React design pattern. Now, what is a React design pattern? It's short for Reasoning and Acting Design Pattern. It's a core concept for building advanced agents in LangChain. It's a method that enables a large language model to become a more capable and autonomous agent by making it think and act in an human-like manner. Instead of generating a final answer in a single step, a React agent follows a cyclical process that combines reasoning and acting. So this is the prompt in the React framework. So here we have all the tools, and these are the use the following format. So here the question, like the input question you must answer. Here we have placeholder for question. Then a thought, you should always think about what to do. Action, the action to take should be one of tools name. So from all the available tools, it should take action. Action input, the input to the action. So whatever input parameter that are needed for a tool, that will be action input. Observation, the result of the action. So after taking an action, after executing an tool, whatever result we are getting, that is the observation. Then thought, I now know the final answer. So if we have the final answer, give the final answer. So thought, this is the agent scratchpad. Now let's understand this React framework by taking an example. So here, let's say we have this. This is the task. Now find the current population of the capital of India. So what it will do? It will take this user query. It will add that query to an agent scratchpad. So right now the agent scratchpad is empty. Now first, let's say agent thinks to take an action. So it will select the tool and execute the tool. Then after, it will collect the observation and update the agent scratchpad, and then it will send the scratchpad after combining with user query to the agent. Now if the agent thinks that it has the answer, so it will go in this route and it will give the final output. Now let's understand all these steps one by one. So our question is, find the current population of the capital of India. So first, agent will think like, I need to find the capital of India first, and then I need to find the population of that city. So action, search tool, because here we have a search tool. We need to find the capital of the India. Now for this search tool, the action input will be capital of India. So we are searching these terms. Now after executing the tool, we have one observation. Now the observation is Delhi is the capital of India. Now after getting the observation, the agent is updating the agent scratchpad. So here, this is the question, this is the thought, this is the action, and we have taken the action, we have given the action input like capital of India. And after getting the result from the agent, we have the observation that is Delhi is the capital of India. So now the scratchpad is updated. You can see. Now we'll give that scratchpad and we'll combine that with the user query and give that to the agent. So now the agent will think like, I have successfully identified the capital of India as Delhi. Now I need to find the current population of Delhi to answer the question completely. Then action is again search tool, but here the action input would be current population of Delhi. So here, now we execute the tool and we collect observation. So here the observation is the population of Delhi, the capital of India, is estimated to over 33 million in 2023, making it the most populous urban agglomeration in the country. Now here we have the we collected the observation. Next step is to update the agent scratchpad and again give the scratchpad with plus user query to the agent. So here this is our updated scratchpad. You can see we have the question, we have the thought process, then here we have observation, then we have thought process again, and we have the observation. Now we will give this scratchpad plus user query to the agent. Now here agent has everything, and then thought I have all the information I need. I will now synthesize the observation to provide a final answer. And the final answer will be the current population of Delhi, the capital of India, is estimated to over 33 million. So this is how this React framework works. Now let's code this entire framework. So here we are setting up our OpenAI key. Then here this is our LLM, and then this is our search tool, DuckDuckGo search. Then here we are pulling the React framework from LangChain Hub. React agent is created using LLM tools and prompt. Then using that agent we create agent executor. So this whole pipeline is getting controlled and executed by the agent executor. Now this is our task, and this is how we are invoking. So if we run this, you can see the thinking process. You can see the scratchpad is getting updated. Okay, the specific population of New Delhi is 25 was not found. Okay, let's run this again. You can see we got the final answer. So guys, I hope you understood the agents in LangChain. Please do comment if I missed something or if you have any doubts. Also, please do like, subscribe and share. I will see you in the next video. Till then, take care.